I'm Josh Poduska. It's great to be with everybody today. I'm the Chief Data Scientist at Domino Data Lab. Very happy to be here speaking to you. The topic that I'm speaking on is one that's kind of near and dear to my heart. It's a little bit of a pet project of mine in data science. A little bit of my background. I've been in analytics, data science for about 18 years. Started out with a math stats background. I used to call myself a statistician. And then at one point, I realized I could make more money if I called myself a data scientist and did the exact same thing. So I said, all right, I'll be a data scientist. So interpretable models. This is going to be a little bit hands-on, like I mentioned. I feel like this is going to be the seminal issue of data science over the next decade. Maybe that's too strong of a statement. It'll be one of the seminal issues of data science over the next decade. Being able to explain your models, being able to manage ethics, bias, misuse in the models that you build, both for your customers and for regulated industries. If you're not able to help your customers understand models, one of three things is going to happen. One, they're not going to use your models. It'll be shelfware. They're just not going to trust it. Two, they will use them inappropriately. And three, well, I guess it's kind of related to the other one, is they'll use them, but they won't trust them. So you have this continuum between I don't use it at all, I use it and I'm blind, I use it inappropriately, or I use it but I don't really trust the insights it's giving me, so I'm not all in. As I mentioned, model ethics, bias, and misuse are going to be key in your lives as data scientists. How many of you are data science or analytic practitioners? Hands on keyboard folks, great. Okay, most of you. So this talk is right geared towards you. If you're not already in a regulated industry, you will soon be from a data science perspective. That's my belief. I think that there is regulation coming for all of us. If you're in banking, you've already been under SR 11.7 since 2011, which has to do with building guardrails around banking models in terms of risk. You might have heard of the Future of AI Act in 2017 in the US Congress, where they basically were studying the impact of black box models in AI and machine learning. And then there's other regulations as well. And of course, trust and understanding. As the last speaker so eloquently put it, we have to put our customers first, especially our internal customers. And they need to be able to trust and understand the models that we're building. So if you can see this, hopefully it comes through. What we're doing is we're explaining the miracle that happens in the process of data science. You might have seen this before if you've studied the LIME paper, L-I-M-E. This is what's called a superpixel inside of a greater image. So it's just part of an image. Think to yourself real quick, what is this a picture of? If you already know the answer, don't blurt it out. But could you tell what this is a picture of based off of that superpixel? In LIME's interpretability engine, this is a superpixel that they use to classify this entire image. And you'll see in a minute what the answer was. An important concept before I go too much further. When I first started studying explainable models, interpreting black box models, I came to the realization that there's a binary view of the world. There's two different ways of approaching this. One is with global explainability, and the other is with local. And I thought this was a very important concept, and I've seen this justified or played out more and more as people are starting to research this in academia, and it's becoming more of a true concept of study. And that is, with global interpretability, you're looking at an entire system, the structure of an entire system. You're trying to explain how that system works. You're trying to find the magic function that describes what you're trying to study. With local interpretability, you're looking at one point instance. One prediction, you want to explain that one prediction. So keep that in mind, because that really is a big dividing line when you're talking about explaining black box models. You need to know how much global interpretability your customers need, and you need to know how much local point estimate interpretability your customers need. Here's a little thought experiment. If you had to choose only one of the following three models to classify all these little images, which one would you choose? So here's your three choices. A model that was able to classify all these images correctly, a model that told you what features of images in general, kind of across all of them, are most important for classification. Or last, a model that told you exactly why a certain image got its classification. Yeah, the answer is it depends, exactly. But the point is, it could be 3 different models. It could be 3 completely different models to answer those 3 different questions. So a model with high accuracy is going to tell you, hey, that's a hat, that's a wheel, that's a bag. A model that, number 2, is interpretable with global inference. That's going to tell you things like, hey, if you drop down to this planet and you're looking at these images, I want to understand what this planet, how it works. You say, hey, in general, green objects with varying edges tend to be plants. In general, if you got a lot of blue in the background, that's usually taken outside, either sky or water. So you get some generalities out of it, some global inference. And here's that superpixel. It was actually a cat, but the model predicted that that image was a black bear based on that little superpixel. It didn't take into account some of the other information in the image that could have told it that it was a cat. But with local inference, like the Lime package in this case, you can understand why the model gave the prediction that it did. So here are just some really easy, just some simple examples of how situations that might play out for predictive, explanatory, or both. This is by no means gospel here. I mean, day trading of stocks maybe shouldn't be put under predictive. My thought here was, if you look at the things under predictive, these are cases where we have a high volume of predictions that we need to make, and humans can't really be in the loop. Has to be automated. Explanatory is where humans really need to be in the loop on this, and it's one-time, big cost decisions. Right? On the predictive side, each of those little decisions probably has a small value, but in the aggregate, the value is huge. Explanatory, usually they're smaller number of decisions, but each decision has a big value. And then most of the time, I think we're in the both case, where we need to explain a little bit and predict a little bit at the same time. So let's get into that a little bit more. A couple years ago, I was asked to help consult on a project where this company wanted to determine predict, they said, root cause failure for diesel engines. They want to predict root cause failure for diesel engines. They said to me, can you help us build a predictive model for this use case? So all right, let's talk about it. As any good consultant does, you ask a lot of questions. And so why are you wanting to predict? What type of data do you have? It turned out that the data they have is short-term test laboratory burns of these diesel engines under high stress conditions. And they could in no way extrapolate that data out to solving the problem that they wanted to solve, which was, how do we predict when diesel engines are going to fail? What they could do and what they actually wanted to do was understand what factors were important in the burnout of engines and how those factors interrelated together. So I told them, you don't want to predict using the wrong word, you want to explain. You want to build an interpretable model here. And once we made that decision, everything else subsequently changed. In my experience, I'd say about 80% of the time, you want to do both, interpret and predict. About 15% of the time, it's, hey, just predict and who cares? Make it a black box. I don't care. I want good predictions. And then about 5% of the time, you're back in the world of statisticians, and all we want to do is interpret, and we want to build a solid statistical model and more like a research project. This varies by industries, but in my experience, this is how it's been. In the future, we might get to this point with all the automated cars. I really like that cartoon. The purpose of this section is to motivate the need for black box models. I don't think I need to do that with this crowd. There are some modeling problems where a linear model is going to do great, and the more complex, more black box models on the right are going to do just about the same, maybe even a little bit worse. And there are times when the data space is so weird. This is like a circular data space with the reds outside the blues, when you really are going to need a complex model, a black box model, to explain and get good predictions. And a linear model just isn't going to do it for you. So let's dive in and explain these black box models a little bit, and interpretable models. I think this is a really important concept to start out with here. Let's suppose that there's a theory that states that inputs X cause response Y via function F, all in caps. And then let's take a little x and a little y, and those are measurable variables that correspond to samples taken from big X and big Y respectively. And then let little f be a model that approximates big F. Okay, so all the little ones are approximations. Interpretable modeling tries to find the little f that best explains the big F. You're trying to find the best function you can to approximate this real world phenomenon, this real theory. Predictive modeling is totally different. There are no capital letters involved at all. It's just you're trying to find the model, the little f, that best predicts future y's. And you don't even care why those y's are there. You just want to predict them well because there's money involved or some value involved in predicting those y's properly. The holy grail, of course, is to find a little f that both theoretically approximates that big F and also predicts little y very precisely. But the bad news is you're not going to find that. There has to be a trade-off between those two. And in the excellent book, Elements of Statistical Learning, which hopefully some of you are familiar with, if not, you should be, Hasty, Tibshirani, and Friedman go through that. These slides are going to be available later, so you can grab all this information. So you got to make trade-offs. Let's get into the nuts and bolts of this. How do we actually do this interpretation? So there's some oldie but goodie methods I'm going to show you first. They still work. They're not very exciting, but they're there. One of them is build a fully specified model. GLM, right? Or GLMM, generalized linear mixed models. You got a whole family of models there that can be very flexible and can be fully specified. So if I'm trying to predict housing price like I'm doing here, I can break that down into exactly how much did square footage, bedrooms, and I can't even read my own notes there, the last one there. I guess that's the prediction. How much did each of the square footage and bedrooms, how much did each of those contribute to the overall prediction? And you can actually really, really break that down for your customers, fully interpretable, very easy to understand. And this, by the way, is an example of local interpretability. We're explaining one prediction. These same models give good global interpretability as well when you analyze the coefficients. Hopefully all of you know how to do this, and this is a simple linear regression. You interpret age. As age goes up in one unit, and this is an example from the amount of oxygen I think consumed during exercise. As age goes up 1 unit, the oxygen goes down by 0.165 units. Holding all other variables constant. That's the interpretation. That's a really strong statement if you're thinking about interpretable statements. So there's some really strong global statements you can make about this system with a fully specified model. Other things you can do is response surfaces. You can have a response surface of the predictions and also of the error. And then you can look at local areas of that response surface to get a feel for how much error, if you're in a high error zone, if you're in a very high precision zone of your modeling space. And you want to be careful with this one because if you have a whole lot of variables that are important, this might be misleading, but if you have 3 or so variables that are really your big ones, you can do a 3D plot of those variables and look at the colors and the changes in the response surface there as well. That gives you a feel for what type of system you're working with from a global level. Decision trees are great. In some industries, like the medical field, some clinicians and practices rely quite heavily on decision trees to interpret their predictive models. You can do things like local prediction bands, partial dependency plots are great, and of course the good old variable importance as well, which gives you a kind of a feel for global interpretability. So those are some ones that you all probably know and love. Don't forget about those, they're great, but the point of this talk is, hey, what's new? So what are some new things out in open source and out in industry? So first, let's get into Shapley values, or SHAP. This is a library in Python that I'll show you here in a minute with a notebook, and we can play along together. So this was, the research here is done by Scott Lundberg out of University of Washington. So the idea of SHAP values, basically the best way to explain them are, the technical definition is the average marginal contribution of an input across all possible combinations of all the other inputs. So basically you're doing an exhaustive search of all the input, all the combinatorial factors, combinations of the input space, and determining precisely how much that input matters to either the point prediction or the global prediction. That's very computationally expensive. So what SHAP does is it has some nice optimization routines for certain modeling types, especially tree-based models, to get you to that answer very quickly. But because it is so sound and exhaustive, they can claim all these technical properties about how great they are, and they do in their papers. But the one thing to remember is when you implement in Python, it's still an approximation. They don't go through the exhaustive routine. But I like SHAP a lot. Here's some of the output from SHAP. So you have this thing called a force plot, which you have, if you see on there, you have the average model score, and then it shows you how much further higher or lower all of the inputs push. For this particular point instance, so this is local interpretability. For this point instance, how much have we been pushing higher or lower based on these inputs? So this is the Boston housing data, and LSTAT has pushed the prediction higher from 22 up to 24. And then, of course, you have in image recognition and deep nets, you have some kind of pixel influence graphs that you get out of SHAP. You also have some decent global interpretability with SHAP, which is global interpretability you're going to find is really hard to do. One thing I'll point out here, these are just showing Shapley values based on kind of different breakdowns. One thing I'll focus on is that variable importance plot. The Shapley authors have, SHAP authors have a real good justification for why you should never use variable importance from XGBoost or random forest anymore. So stop using those and always use SHAP variable importance. They show under certain conditions how the variable importance graphs under those other mechanisms can give wildly different answers, whereas if you use them under SHAP, they're much more stable and more dependable. So in my work, I've gone away from variable importance plots based on those other techniques. Lime. So Lime is a very interesting technique. It came out before SHAP. At least I got a hold of it before SHAP. I think it was first. It builds local approximations to a black box model, which makes a lot of sense, right? You got this black box model. You don't know how it works in all these corners. Let's just build linear models all over the place. All these linear models, and let's model how the world works in that little space. And then with our linear model, we can tell exactly what's going on, and we can give good interpretations. So the graphics are a little bit different. It does a little bit better at giving like super pixels rather than just all these itty bitty pixels together with the deep nets. And also one thing that is kind of hard to see, but on that y-axis there, it gives you ranges of each input. And it says, hey, LSTAT was important because it was between 16 and 17. That's why it pushed this value higher. SHAP doesn't give you that. Something that the linear model has a little bit more flexibility with. And we've got some links I can share with you later. Okay, so TCAV. You might have heard of TCAV. It's a really great tool for deep learning interpretability. It uses a concept called directional derivatives. The way it works is you take another, just like Lime, you take a linear approximation to a certain part of your network space, and you provide it with counterexamples to a particular concept that you choose ahead of time. The example they always use is zebra and stripes. So we're trying to classify zebras in all these images, and we want to see how much the concept of stripe is captured by our model. So does our model rely on stripes to predict zebras? So we get all these examples of stripes that we feed the model, and we get counter examples of non-stripes that we feed the model, and we take the orthogonal vectors of stripes and no stripes, and we measure things in our model at that point. I'm probably doing a bad job of explaining it, but it works for global explainability, not point estimate. It's for the whole model structure. You're trying to figure out if your whole model is reliant or usually biased to a certain concept. And it only works on images, at least it's mostly been tested on images. It might be able to work on other networks too, but they haven't dove into that yet. Here's just a little narrative they give. So you see, you'll get pictures of stripes. You'll feed that to the model. You'll get pictures of non-stripes. You feed that to the model, and you run through this TCAV comparison to get an output score of how important stripes were to your model. It's not a push button solution, unfortunately. Hopefully soon there'll be an open source package that makes it easier to use. You can use it now, but it takes a little bit of work. You have to find the concepts yourself of stripes and find the counterexamples yourself. They recommend 50 to 200 or so. You have to pick the model layers you want to test this at, and then you have to write your own wrapper function for loss, and you have to write your own class to return your activation. So a little bit of coding involved, but they walk you through how to do it. A couple other points to keep in mind here. TCAV only works if your network has learned about that concept. Might be a no-brainer statement, but if you're trying to test stripes versus non-stripes, you might get really weird answers if it hasn't learned about stripes. Let's move on to this one. So this gives you a view of what the output of TCAV looks like. It's basically just bar graphs and numbers. So this top one's interesting. They're trying to classify, or trying to see how much the concept of a ping pong ball is used in classifying race. So we have Latino, East Asian, African, Caucasian. Are any of our models biased to the ping pong ball associated with race? Is there a correlation there that our models have picked up on that they shouldn't? And you can see that the green model is being biased towards East Asians as well as the orange model. The blue model does a pretty good job of distributing, of not worrying about ping pong ball when it's classifying race. So you can compare this to the actual breakdown of race in your data set. So it's a pretty cool concept that it can do this for deep learning models. And down below, one about apron and gender, and some other examples as well. So a lot of good reading you can do later on TCAV. This one is interesting. This is out of CMU. I happened to run into the CEO of this startup company called AI Lens. He has what I think is one of the best ways to give local and global interpretability for deep nets. The concept is through influence-directed explanations for deep nets, so it works on convolutional neural nets. What you do is you take the traditional way that Shap and Lime do image explanations by looking at pixel influence or superpixels, and you combine that with something called activation neurons. So the pixel influence, the TCAV authors get into this. You shouldn't really be using Shap and Lime for image explanations. The pixel influence metrics and visualizations they usually don't change much instance to instance within a model. They're usually kind of set, and they don't really give you good interpretations. This one AI Lens gives you a much better way of doing it because it combines that pixel influence with activation neurons for higher level concepts. Here's an example. So each of these car images, we're trying to predict whether it's a sports car or a sedan. And what it's doing is it's looking at the hood, at the hood or the top part of the car. So this can tell you this particular model is focusing in on this part of my images across all my images, and it gives you a feel for how your model is working under the hood. And also it gives you local interpretability because you can look at each image and see the superpixel as to what's important there. And you see it's not as well defined as Shap and Lime, but it's more reliable. All right, and the last one I'll show you before we jump into the notebook is AdTree. They're changing the name. Well, no, it used to be called MediBoost. They're changing the name to AdTree. This is Dr. Valdez. I went to at UC San Francisco. I went to a talk there, just happened to stumble upon it where he was speaking, and this is the coolest thing ever. So this is not all right, I built my model, let's go explain it type of approach. This is let's explain while we're building the model. And that made a ton of sense to me. Why aren't we trying to redo the math a little bit so that we can predict and explain at the same time? So that's what he's doing. And he's saying, hey, let's rethink decision trees. Instead of building a random forest, why don't we have one tree where each node is an ensemble? Each node is like a random forest. Each node is a gradient boosted algorithm. And let's build that out so at the end we have one tree that we can then explain the world from, but we still get pretty good prediction accuracy. Very close to a gradient boosted tree or a random forest collection of trees. So I thought that was a great approach. He's got an R library for it out there. I won't get into all the details here, but basically he proves that gradient boosted trees and cart live on a continuum, and he's able, with one parameter, you have a parameter for explainability. And you can tune that parameter as you want. It's kind of cool. What you get out at the end are trees or a rule set to explain your world, but it gives you much better prediction accuracy than a single decision tree. But you still have one decision tree to explain how things work. Just so you know what a few other companies out there are doing, I gathered these. Some of these are our customers, but this is not inside information. This is what I've gathered at talks they gave at Strata or other talks, other conferences. So Lloyd's uses Shap and Lime a little bit, but they're mostly sticking to generalized linear models because they really want good interpretability. FICO recently had an AI challenge, but all of it was in that unexciting section. They're not using Shap or Lime or any of the new stuff yet. It was all partial dependency plots and other ways to explain models. Bloomberg is also sticking to generalized linear models for now. And they tested recurrent neural networks for some of their NLP stuff, but they're hesitant to use it in production because they really need explainability. So there's big problems out there that people are not using the best tools available because they need explainability. Love this quote from Yogi Berra. So I'm going to end these slides with a couple of tips on what to do in the future. I put this together. This is just me, my thoughts. Again, I'd love to hear what other people think too. I plotted predictive power by general interpretability. The size of the bubble is how frequently I see these techniques used out in the industry. And just to let you, I think it's good for all of us to know the modeling approach that we're using. Where does it fall on this continuum of being able to predict well and being able to explain well? So of course, neural nets are going to give you the most predictive power, generalized linear models, the most interpretable power, and you got everything in between with things like stepwise regression probably not doing good at either. And then lastly, you can look at this later on, but this is kind of a decision flow that I use roughly. For when I need to predict, I go all out and just use neural nets, accuracy at all costs. If you need to interpret only, then if you have image data, you have TCAV and AI lens. If you have structured data, you can either if you can collect data, do a design of experiment. And then where we're usually at is up top with interpret and predict at the same time. If you can collect data, I like to start with a generalized linear model and then maybe build from there. But usually if you can collect data, you can design the experiment well and get good predictive power and explanations. The hardest part to do is when you have observational data, you can't collect it, it's handed to you, and you have to get global interpretability. That's really, really hard. What I recommend to do is start with a generalized linear model. It gives you a baseline, it gives you an interpretation, and now you know how much more predictive power you can squeeze out as you go beyond that. You can try tree methods, naive Bayes. They kind of are a good balance between predicting and explaining. Or you can just go all out predictive and then use tools like Shap and Lime or TCAV and AI lens to give you interpretability. Okay, let's jump over. So if you have your laptops out, you can follow along, open up a web browser. And I'm going to show you where to get some notebooks that go into Shap and Lime. And also you can get the slides from this area as well. So if you go to dominodatalab.com, I'm going to put you into Domino's trial site. In the trial site, I've loaded a project for explainable AI. So go to dominodatalab.com, and you're going to click on, up at the top, Get Started for Free. You can use Google or LinkedIn to get into it, or you can fill it out with a different email address if you want. I'm already signed up, so I'm just going to sign in. Cool. Once you get in, it should look something like this. Thank you. There we go. Thank you for that. So let me go back. I thought you guys were seeing this. So on Domino's website, you'll click get started for free up the top. And then you can log in with Google or LinkedIn, or you can just fill out with a different address. Okay. And let me log in again. There we go. Okay. Once you're in, it should look something like this. Let me make the resolution a little bit bigger. All right, cool. You're going to have projects. If you're in for the first time, you'll have like 4 projects or so. Shap and Lime should be one of them that we preload in there, so you should see that there. You can start new projects. You can search for other people's projects. There are lots of people on there doing cool stuff. I'm going to go ahead and dive into Shap and Lime. So you get a README real quick with links to a couple blog posts that we found helpful. If you click on Files, you might see the PDF, or you might not, depending on whether my preloading of the PDF worked. If it didn't, I have another project that has the PDF, and I can get that to you. Is there? All right. So if you logged in a long time ago, it might not be there. So what I want you to do is click on Workspaces. And let's just take Jupyter Lab, and let's start that up. Cool. So what it's doing now is it's spinning up a Docker image that's preloaded with Shap and Lime and a bunch of other Python and R libraries so that you're kind of ready to go and ready to hit the ground running. And you can, in Domino, you can configure these environments for different use cases like deep learning or whatever. All right, off to the side, I've got my notebook here, my Shap and Lime IPython notebook. Just going to open that up, and we'll walk through it here. So we're going to start out by loading some libraries, and then I've got versions of Shap and Lime. Some of this version stuff might not be in your notebook, because I think I might have added this later myself, but we can look at the versions. So hopefully everything works here during my live demo. And then what we're going to do, and you know what, I'm going to actually, after these first 3 run, I'm just going to run them all because there's one cell that takes a little while to run. So we're going to use a Boston housing data to go through this. All right, there, so they all ran, those 3 ran. I'm going to run all cells myself. And we'll just jump through them. So first thing we're doing is simply using train test split from sklearn to put the Boston housing data into xtrain, xtest, ytrain, ytest. Here's a quick snapshot of it. We're going to put the, just to show you what the y data looks like. Here's a description of the data set. I'm going to skip that for now. All right, so first thing we're going to do is build the models. So let's start by building an XGBoost model. So it's a simple XGBoost model. It's Boston housing data, so it's not a classification problem, it's a regression problem. So this is from the XGBoost library. Then we build a similar model, but from the scikit-learn library. So we have 2 gradient boosted tree flavors here, one from XGBoost, one from scikit-learn. Okay, so XGBoost model and sk_xgb. Then we got the random forest model here. So this is from sklearn. We've got k nearest neighbor, again from sklearn. So those are the 4 models, I think those 4 that we're going to use. 2 XGBoosts, a random forest, and a KNN that we're going to use to explain. So now let's start by creating the Shap explainers. So it's quite easy to do. There's a Shap library, shap.treeexplainer. So we have to choose an optimization routine that we want to apply to this particular problem. And with XGBoost and with random forest, we want to use a tree explainer from Shap. So that first line builds the explainer. The second line puts, we get the Shapley values for test and for train, because we're going to use those in a minute. So we do that for both flavors of XGBoost. We do that for random forest. And now here's the part that takes a while, is for the KNN. So as I mentioned, Shap is an approximation, and if they don't have a certain approximation built, It's a very exhaustive process to go through all the combinations to get the Shapley values. So with KNN, there's no approximation built for SHAP. So you have to go through an exhaustive process. So what they actually have you do to start is they want you to build a k-means summary of the whole data set. And then you actually use that k-means summary that you model against, which that makes me feel weird. I don't know if the k-means summary of a data set is going to give me good interpretability. But that's what they have you do. So this is going through right now and building that k-means and then applying the KNN to that k-means. And it's probably mine just now finished. But you can see all the work that it went through. And this Boston Housing is a very small data set. So you can imagine how much time this would take on a larger data set. So there are times when the SHAP explanations are just prohibitively slow. Wow, this is a long time. There we go. All right, so without k-means, it took me well over an hour. With k-means, it takes a couple minutes. And again, Boston Housing is a very small data set. All right, now that we have all those SHAP values, all I do in this cell is put everything into a data frame. So just the SHAP values go into a data frame. That's all that's happening here. And now let's get into Lime. So what Lime is actually quite easier to use. So the first thing we do is we need to tell Lime what are categorical features and what aren't. So we start with that. And then there's one explainer for all models. You don't have to build, Lime doesn't have these optimization routines for tree-based models and for all the other types of models. It just has one way of doing local interpretability with all those local models. So we build that one explainer. And now we're ready to go. So let's explain these instances. I'm going to pick just the first instance, j equals 0, for all of the explanations. So here's the first one. With SHAP, this is a force plot. We're explaining the first prediction in the Boston Housing data set. And we can see that the default base value was 21.83, and the first instance was predicted to be 22.92. And the reason why is because LSTAT was high. That pushed it up most. And on the other side, number of rooms and tax pushed it down the most for that particular instance. We have a very solid explanation for why that particular instance predicted the way it does. Let's look at what Lime did for that one. Well, out of the box, Lime cannot work on the XGBoost library, at least with the version of Lime I have. So Lime didn't give us anything. So I threw this one in on purpose so that you can know where the potholes are. So let's get into the next library, which is scikit-learn's version of XGBoost. SHAP gives you a very similar explanation because it's a similar prediction. And Lime looks a little bit different, but I actually like the Lime output here. I wonder if you like it better as well. But so the predictive value, it shows you where the predictive value lies between all predictive values. It shows you which ones had a positive effect on that prediction. So PT ratio, LT stat, and again, it says PT ratio because it was less than 17, LSTAT because it was between 6 and 11. And these are the actual values down here. So compare that again to that. So it actually had PT ratio as a higher influence in Lime than it did up in SHAP. So they disagree slightly because they're using different approaches. When they disagree, I usually go with SHAP because it is a little bit more technically sound. But there are times, like we saw, where SHAP just won't work. It's just way too computation expensive, so it's good to have Lime as an option. All right, and then these are all going to look similar. Here's random forest, similar plots, and the k-nearest neighbor, similar plots. And then here's the syntax, very simple syntax for doing a summary plot or a variable importance in SHAP. Again, this is what I would use instead of XGBoost random for variable importance and instead of random forest variable importance. Stop using those, start using at SHAP's variable importance. It's much more technically sound and more stable. This summary plot gives you a decent feel for kind of what's going on in the whole system. How does LSTAT affect the SHAP values? So higher, this goes from, looks like about -7 up to 15. 15 means it has a high impact on moving the prediction higher. So a lower value of LSTAT moves the prediction higher. So, right, that gives you, this is a good alternative to coefficient analysis, right? if you have a black box model, you can't get the traditional linear regression, logistic regression, coefficient analysis, this is the next best thing. It's not bad. If you're putting this in front of your internal customers, you might need to do some translation from this to them, put it in their words, but it gives you the information that you need. And it tells you, hey, LSTAT can swing things a lot. So can rooms. Whatever these last ones are, not so much. They don't swing the prediction that much. So it also gives you variable importance as well. Pretty cool plot, actually. And then you get a dependency plot. How much are we moving things LSTAT by tax, colored by tax, for example. So you have the SHAP values on the y-axis, how much is the prediction moving, and you have the actual LSTAT values along the bottom. The last thing I did for you, which you can use if you want, is I really liked this plot, but I thought, hey, for local interpretability, it'd be nice to know which dot I'm concerned about. Which dot am I predicting right now? So I just wrote a little function to put the dot on there. So you can see the big black dot. That's the first instance. That's where we are in the whole world of this model's prediction. Okay. So that, I went through that a little bit faster than I normally do. Like I said, usually that's about 90 minutes material, but I want to condense it down. So you can play with this notebook on your own on that trial site. And if you have any questions or comments now, I'd love to take them. Yeah, I'll repeat the question for the video. Does SHAP take into, are you talking about interactions? Does it take into account interactions? I don't think it takes into account SHAP does not take into account interactions, but it does go through each variable one at a time and kind of holds that one constant and looks at everything else and looks at different combinations of those variables to get a real exhaustive search of the space. So if you know statistics, if you think of like Fisher's exact test for doing the contingency table analysis versus the chi-square, which is like a distribution of some approximation, SHAP's kind of like Fisher's exact test. It just checks every possible combination. It's not so much like a distribution-based approach. Yes, so the question was, you have rooms and square footage or whatever. Those contain similar information. Are they going to get a similar score? Yes, they'll get a similar score because it'll look at square footage without rooms and it'll look at square footage without taxes. It looks at square footage kind of in every possible way it can and gets its pure impact on the model without regard to worrying about any other kind of cross-collinearity that's going on between. But it doesn't look at the interaction, it doesn't create a new variable interaction of rooms and square footage. You have to do that on your own and then feed that to SHAP. Yeah. Okay, yeah.
Hey, Josh. My name is Raghu. I manage the data science team at Discover Financial Services, and part of my job is interpretability. And I'm supposed to speak with regulators next quarter, so let's see how long the job lasts. So my question is really, when we talk about interpretability, especially when it is customer-facing, not necessarily just a prediction, Lime and SHAP have, when we talk about local interpretability, they might be good at that particular area level, but some of the global interpretations might not hold. For example, if you have delinquency in your history, delinquency is a bad thing, but it might end up in the local interpretation as a good thing, which might not go down well when we give a decline reason for a customer. So what are your thoughts about using these kind of interpretable techniques when it comes to, financial services?
That's a great question. I actually hadn't thought about the scenario where a particular variable, the goodness or badness of it is going to be different depending on whether you're looking at local interpretability or global interpretability. But that's a great concept. That's so true. First of all, I'll say that I mentioned it once, but then I think I didn't mention it, or I didn't hit on it later. Lime doesn't really give you anything for global interpretability. It's just local interpretability. Because SHAP looks at the whole space, it can give you some of those alternatives to a coefficient analysis and the variable importance plots. So to answer your direct question, it's going to be completely dependent upon the model, right? And you're going to have to do a lot of translation from math stats into everyday language to your stakeholders. But I think that's a great comment that you made for everyone to be aware of, and myself included, that some factors are going to change their importance and behavior and goodness or badness depending on what state you're in. I don't have an answer for you on how to solve that problem, no silver bullet. But you can use SHAP to explain it in a global term, but then you run the risk, if you're talking to executives, that they might think that delinquency on over a certain term is going to be bad, but in other situations it might be good, and they might lose sight of that. So it's just going to have to be, I think, just have to be education. I'll think about that though more. It's a really good point. Yeah.
My name is Andre. I'm a software developer at JP Morgan. I was wondering if you could explain the difference between convoluted neural networks and recurrent neural networks and the use case for each of those.
Sure. Yeah, it's not super attached to the topic here that we're talking about, but convolutional neural nets are used more for image classification traditionally. They can do a number of things. It's more just a traditional way of stacking layers in your network up until you start real big, and then you kind of group things in certain ways, and it has a way of going through and summarizing some of the inputs in all the different layers so you don't have so many parameters at the end, and then giving you a prediction. And recurrent neural nets kind of have, as the name implies, a recurrent nature to them. They'll circle back through things. They're really good at more text analytics, natural language processing. And they have different components set up in there to kind of loop back through. And that also leads into memory-based networks where you kind of have a memory and get a sense over time of how things work. There's kind of an evolution there. But we can talk more about that afterwards. Yeah.
Back to the beginning, I think you defined machine learning. It's looking like a function approximation. You map from a domain, to the, to the independent variable, to the dependent variable. So then you talk about interpretability. So to my understanding, if you can write out the function, in an explicit form, mathematical form, like x plus 2x2 squared, stuff like that, then you can interpret it. So linear model is one of the best example. But then on the other side, the spectrum, you can only have the implicit function. You give up input, you get output, but you cannot write the function explicitly.
Black box, yeah.
Yeah, black box. So, and you mentioned in the book, I understand it's no free lunch. You cannot get both. But you mentioned the book, Elements of...
Statistical learning.
Oh yeah, I know this book is very mathematically rigorous. Mm-hmm. So has this book proved with mathematical rigor, no free lunch?
Yes. Yeah, you can look at, on the first edition, I think it's page 193 was in my notes there. You can go look at that, and they prove with mathematical rigor that there's no free lunch. Yeah. They're doing it in the concept under certain assumptions. But you can go check out that page for the given assumptions that they put in there. But there's no free lunch.
Another question, SHAP or whatever. So you are talking about some models where it can measure the interpretability. So I don't see you mention the darkest box, neural network.
Yeah, we did mention neural nets, but you're right, I didn't go into it too deep, especially not in my notebook here. SHAP and Lime will both give you interpretability for neural nets. You'll see the little pixels that are highlighted on those images that you saw on some of the slides. That's telling you, SHAP and Lime are telling you, hey, those pixels were most important in giving the prediction. But there's been recent work that says that their approach to interpretability of neural nets is not accurate because the pixel influence-based explainability models don't hold up over stress testing. To put it simply. So it's recommended, they're better than nothing, but it's recommended to use something like TCAV or AI Lens or these more modern approaches. And this is a deep space of research. This is a big space of research in academia. There's stuff coming out all the time. I put these slides together probably 5 months ago, and I bet you there's new stuff out there right now that I need to update it for, and I just need to spend a couple days seeing what's the latest and greatest, because there's stuff all the time that's out there on deep nets.
And actually, just to correct on that, there's new stuff out there. The no free lunch thing, I want to correct. That is